We've seen two different approaches to parameterizing rotations. I've called these coordinate systems. So for example, using rotation matrices, you can represent rotations with a set of 9 numbers or 9 coordinates. Those coordinates are redundant, so in reality they are not really coordinates. We've done the same thing with Euler angles, where you get a set of 3 numbers or 3 coordinates. We're now going to look at a different way of looking at rotations. This involves explicitly representing the axis of rotation and the angle of rotation. The key idea comes from a theorem due to Euler. Euler said that a displacement of a rigid body such that a point on the rigid body, say O, remains fixed. And by the way, that is essentially what a rotation is, a displacement that leaves a single point fixed. Well, this rotation is equivalent to a rotation about a fixed axis through a point O. Notice that a description of a rotation doesn't really talk about an axis, but what Euler is saying is that any rotation is equivalent to a rotation about a fixed axis through a point O. Let's see how to verify that. In order to do that, again, we're going to consider displacements where the point O is fixed. So here are two positions and orientations, and I'm going to translate the rigid body from the second position and orientation so that the two origins are identical. So the point P has moved to the new point P prime. As we've seen before, the vector OP can be written as a linear combination of the basis vectors A1, A2, A3, and likewise the point P prime can also be written as a linear combination of A1, A2, and A3. So now we have two 3×1 vectors, the vector P and the vector Q, that are related by the rotation matrix. What we'd like to do is to ask ourselves if there's an axis that remains fixed under this rotation. In other words, is there a point P such that after the rotation through R, it stays fixed? In other words, the point P is invariant to the rotation. This is the essence of the proof. So again, going back to the basic equation where P gets rotated into Q, the question we ask is there a point P that maps onto itself? If there were such a point, then that point P would define the axis of rotation. Well, if there was such a point P, we can write P equal to RP, and this is nothing but a statement that 1 is the eigenvalue of the rotation matrix R. So we can solve the eigenvalue problem and verify that if Rp were equal to lambda p, that lambda equals 1 is a solution to this eigenvalue problem. And this is easy to verify, and it's a good exercise for you to try. Now I want us to consider the inverse problem. Suppose I give you an axis of rotation and an angle of rotation. How do you calculate the rotation matrix armed with these two pieces of information? And note that we already know how to do this if the axis of rotation is the x-axis or the y-axis or the z-axis. In fact, we discussed formulae for these very simple cases. But now we have an arbitrarily oriented axis given by the unit vector u and an arbitrary angle of rotation given by the angle phi. Let's consider a generic vector p, and let's see how this vector p gets rotated if the rigid body to which it's attached gets rotated about the axis u through an angle phi. Before we do that, I want to break this vector up into two components. One that's parallel to the vector u, and the other that's perpendicular to the vector u. the one that's parallel to the vector u, I can obtain by projecting it along u. And then if I subtract that projection, I get the vector that's perpendicular to the vector u. Now it's clear that the component of the vector that's along the axis is never changed by the rotation. In other words, the vector p dot u times u remains unchanged by the rotation r. But the perpendicular component, which is along v, will get rotated. So I'm going to use now three vectors, u, v, and the orthogonal vector w, where w is given by u cross v, as my local coordinate system, or my local basis. So once again, the vector along u does not get rotated, but the vector along v does get rotated. And this is what it looks like. It's v cosine phi plus w times sine phi. So this is simple trigonometry, and you should be able to verify it. So the vector p after rotation now consists of two new components, one of which is the same as the component before, the one parallel to u, but the one perpendicular to u has changed, and that is now given by v cosine phi plus w sine phi. If I add up these two components, I get the new vector. So now we can derive an expression for the rotated p, and that's given by p times cosine phi plus u transpose 1 minus cosine phi times p plus u cross p sine phi. So that is the resultant expression. Now you have to remember that p is a generic vector, so this expression holds for any vector p. So now we have this expression. We're going to simplify it just a little bit. Notice the term u cross p. Well, the term u cross p is obviously a cross product, but it can also be written as a matrix times p. And this matrix we'll call u hat. So u hat is a skew-symmetric matrix whose components are the same as the components of u. Now we have this expression. Let's remind ourselves that p is a generic vector, and so this expression applies to any vector attached to the rigid body. So the rotation of a generic vector is given by the right-hand side, the formula we just derived. If you remove the vector p from both sides, you essentially get an expression that depends only on the axis of rotation and the angle of rotation. And this is the rotation matrix. It consists of three terms. One is the identity times cosine phi. The second is u transpose 1 minus cosine phi. And the third is u hat times sine phi, where u hat is a skew-symmetric 3×3 matrix. So this formula is due to Rodrigues, and it's called Rodrigues' formula. So the key idea now is quite simple. Given a generic vector u and a rotation angle phi, you can derive the rotation matrix using this closed form expression. And you can verify that this expression makes sense by testing it on some simple cases we've already seen before. So for instance, take u to be a unit vector along the x-axis, and you can verify that the result is the same as a rotation about the x-axis through phi. So again, we can revisit this question. Is this representation a onto representation? Is it one-to-one? It's onto if every rotation matrix can be represented by a combination of a vector u and an angle phi. It's one-to-one if there's a unique representation. Euler's theorem is pretty much telling us that it's onto, because we know for every rotation there's an axis of rotation. What about the one-to-one property? Well, we can immediately see that this does not hold. If you look at a rotation about the axis u through an angle phi, and the rotation about an axis pointing in the opposite direction through the angle 2 pi minus phi or minus phi, you can verify that these two rotations are the same. In order to verify it, just think about rotating a body one way through an angle phi and then the other way through an angle minus phi, and they're basically the same rotation. You can also substitute these into Rodrigues' formula and verify that you get the same rotation matrix. So what if we restrict phi to this interval from 0 to pi? If we do that, then minus phi will not be in the same interval as phi. Likewise, 2 pi minus phi will not be in the same interval as phi. Does this make the map one-to-one? This is something you should think about. One way to explore this question is to look at Rodrigues' formula and then ask ourselves, for a given rotation matrix, can we extract u and phi from this matrix? So to do this, you can verify that if you take the trace of the rotation matrix, let's call that tau, which is essentially R11 plus R22 plus R33, and you subtract 1 from it, you divide by 2, and you will get cosine of phi. And this is obtained by directly applying Rodrigues' formula to get the trace, and you should verify that this is true. Well, if this is true, you can also see from Rodrigues' formula that u hat can be obtained by just doing R minus R transpose divided by 2 sine phi. So you've obtained in this case u without actually solving for the eigenvector. So is the axis angle rotation one-to-one? It's actually many-to-one. Even restricting the angle from 0 to pi does not make it one-to-one. It is one-to-one except for these special cases. The trace equal to 3 is equivalent to cosine phi being equal to 1, which means phi equal to 0. While if phi equal to 0, there is no unique axis of rotation. If the trace is equal to minus 1, then phi equal to pi. In this case, you can have two axes of rotation, either the axis you've obtained using the formula above or the opposite, the negative u. The best way to think about the rotation group SO3 is by imagining a solid ball of radius pi. Any point on the ball's surface or inside the ball essentially represents a rotation whose angle is given by the radius. And the vector that describes the point with the origin of the sphere as the origin of the vector tells you the axis of rotation. Again, it seems like there's a one-to-one map between points on the surface of the ball or inside the ball and the set of rotations. This is true, again, except for points that are on the surface of the ball. So if you look at any pair of points on the ball, but that are diametrically opposite, they essentially correspond to the same rotation.